Okay, here is video 2 of the lectures for week 2 in my fall 2020 DC theory class. I've got this circuit on the board. I've got 3 resistors of pretty radically different sizes, and I've got a much larger source. I've got a 480 volt DC source on this one. Again, this is just numbers we're making up, and we're modeling circuits based on that. And I want to kind of show you a phenomenon that happens when you've got resistors of different sizes in a circuit, in a series circuit. So I've labeled them R1, R2, and R3. And the first thing I do is I look at this and I say, well, do I have enough to do any of the functions of Ohm's law? Do I have the voltage and the current? Well, no, I don't have current. Do I have the voltage and the resistance? Well, I have individual resistances, but I don't have the total resistance. So I'm going to have to do some math before I get there. And I go, oh, wait a second. This is a series circuit. I recognize this because there's only one current path. If I'm an electron and running around this circuit, I don't have any choices. I can only go one way, and that is to go through R1, through R2, and through R3. Again, we're talking about this as grounded here so that we can call this 0 volts. And we can call this 480 volts. So the first thing I need to do is remember that, well, you know what? 3 resistors in series with each other, their equivalent resistance is going to be just their sum. So from our total, I'm going to say our total is R1 plus R2 plus R3. 220 plus 15 is 235, plus 5 is 240 ohms. So boom, I've already solved one thing on this. Now that's my equivalent total resistance. I've got my total voltage and my equivalent total resistance. I can solve for my current in the whole circuit. And I know from up here that I equals E divided by R, which in this case is 480 volts. You can read my terrible writing. 480 volts divided by 240 ohms. 480 divided by 240, again, I made the math easy on this one. Don't necessarily assume I'm going to make the math easy on the ones I give you guys to do. But on the board, it makes it really nice. That's going to be 2 amps. Now, where does that 2 amps live? Well, it's everywhere, because that's one of the rules of series circuits, is that my current is the same at all points in a series circuit. That's really one of the fundamental things that we need to remember and know about a series circuit. I need you to first be able to recognize a series circuit, and then remember that if I can solve current anywhere in that circuit, or in this case, everywhere in that circuit, that is the current individually that I can apply to each of these resistors. So let's go ahead and do that. Let's apply that current here, 2 amps, 2 amps, 2 amps. Now it's just a question of using Ohm's law. And I remember that if I cover up the E for voltage, I'm left with current times resistance. So E equals I times R. E equals I, R, which is the same as I times R. I can leave it out when I'm doing algebraically, those of you who remember that. So in R1, so E at R1, it is going to be 2 amps times 220 ohms. E at R1 is going to be 440 volts. E at R2 is going to be 2 amps times 15 ohms. So E at R2, that is to say the voltage dropped across resistor 2, is going to be 30 volts. Good to keep my units in here so I remember what it is I'm talking about. E at R3 is going to be the same math. It's going to be 2 amps, but this time R3 is only 5 ohms. And that is going to be 10 volts. So let's go ahead and put our voltages up here. On this particular one, I've got 440 volts. At this one, I've got 30 volts. And at this one, I have 10 volts. So I've solved my individual voltage drops. Let's check it with a couple of things. Let's make sure it follows all the rules and I didn't do anything wrong. Well, I know that all of my voltages should add up to 480. That's Kirchhoff's voltage law. Or 480 subtracting one at a time should add up to 0. So let's go ahead and check that. Well, 480 minus 440 is 40. 40 minus 30 is 10. I've got 10 volts to ground here. So I started out with 480 volts to ground. I subtracted 440 to give me 40 volts to ground. Subtract 30 from 40 to give me 10 volts to ground, and then I drop my final 10 volts. So it works. Or the other way, I can add them up. 10 plus 15 is 35. That isn't right. 10 plus 30 is 40 volts, plus 440 volts is 480 volts is my source. So Kirchhoff's voltage law works. Now here's the thing I want you to notice though. It's the proportionality rule on these. Notice that the voltage drop is proportional to the size of the resistor. So as my resistor gets bigger in a series circuit, it drops more of the voltage. So even though this is a big resistor which cranks the current down, by putting this resistor in series with this circuit, I get less current than if this resistor wasn't there, right? Less current is what this resistor does to the circuit, but it is actually the thing that drives as far as voltage goes, because it's all three of the resistors together that determine my total current. And when we start getting into power over here, power is in watts, and power is the current times the voltage. If the current is the same everywhere, and the bigger the voltage drop is, the bigger the resistance, then I'm also going to have the biggest power at the biggest resistance. So what I'm getting at essentially is to remember that the biggest resistor in a series circuit is the one that really drives things, especially when it's vastly different than these ones. So let's go ahead and do power. You guys, I'm not sure we've covered this much yet, but power in watts equals current times voltage. And that's going to be the actual power dissipated at this resistor. Remember, all a resistor does is give off heat. And we can measure that heat that it gives off in power dissipated. We call that in a circuit. Later, when we get into AC and we start talking about capacitors and inductors, we're going to have some other flavors of power. For right now, we're talking about power in watts, and it's true power, which expresses itself in heat. So let's go ahead and solve for power on these. Power is current times voltage. I've got 2 amps and 440 volts. So my power is going to equal 880 watts at this resistor. At this one, I've got 2 amps and 30 volts, so my power is going to equal 60 watts. Vastly different, right? Even though this is a smaller resistor and would let through more current, because the current is limited by all the resistors, this guy gets limited in current here, but it doesn't drop near as much voltage, so it does not dissipate as much power. Because remember, the voltage seen across this guy, if I'm this resistor and all I know is the voltage that I'm receiving, I'm only getting 30 volts because of how this works out. If I'm this poor little guy, heck, I'm only getting 10 volts. So if I calculate power, power equals current times voltage, P equals I times Z, and I'm not writing it out, I've asked you to write it out, so my bad. 10 times 2 is going to be 20 watts. So check it out. I'm dissipating 880 watts at this resistor, but only 10 watts at this resistor. And it's because of the difference in the size of the ohms. Whereas if I put this resistor alone in this circuit, I'd have crazy amounts of current, right? 480 volts and only 5 ohms, I'm going to have, I'm going to have nearly 100 amps in this guy. I'm going to have just shy of 100 amps flying through this, which is a lot, which means I have to put big wire in, right? But the fact that I've got this resistor in here and this resistor in here, it takes my total current down to a really manageable 2 amps. As electricians, we're saying 2 amps, I just run 14 wire. 14 wire is good for 15 amps, so I'm like way under what I need here. However, if I remove this resistor or jumper across this resistor, short across this resistor, suddenly I'm left with just these two, and I would have 15 ohms and 5 ohms. I'd have 20 ohms at 480, which would give me, well, let's do the math really quickly. If I have 480 volts divided by 20 ohms, remember, because I equals E over R, so 440 volts, 20. 480 divided by 20 is going to be 24 amps. Cancel the zeros, 48 2, yeah, 24 amps. 24 amps is a hell of a lot more current than 2 amps. 24 amps is going to require what? Like 10 wire or 12 wire in the 90-degree column, but it's going to require 10 wire. So it's a lot bigger draw, a lot larger current flow when I have those guys. So the takeaway from this is that not only is there a proportional level to how much voltage drop there is in the resistors, but it also is the biggest resistor drops the most voltage. Now this is true of series circuits. When we get into parallel circuits, it's going to be different. I want to show you one other thing with this proportionality too, is that you can see that I have my total voltage, and I drop some of the voltage, and I drop some more of the voltage, and then I drop the rest of the voltage. And these three voltages add up to this voltage. That's my Kirchhoff's voltage law, right? Well, there's actually a mathematical formula that I can use to, instead of doing Ohm's law, which I prefer you do. Ohm's law is really great, and we can use it all the time, and that's the beautiful thing about it, is it works in every situation. But I can also say, well, you know what, I want to know what the voltage is here at R2. And I know that R2 is 15 ohms. And I know that my total resistance, because I did that math, is 240 ohms. So here's the proportionality. If I say that, well, this guy is 15 out of 240, it is 15 240ths, if you want to think of it as a fraction, 15 240ths of the total E, or source. So here's the formula. So E at R2 equals R2 divided by R total times the E source. And I kind of mushed those two together, but you can see what I'm doing there. This is R2's value, and this is R total's value. R2, as seen as a ratio of the total, multiplied by E source will give me that. Let's try it really quickly. Again, calculators, where the hell's mine? Here it is. Clear, 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 on. This is how I would do this in my calculator. Instead of doing the parentheses and everything, I'm going to go 15 divided by 240, and that's going to give me a number. In this case, it's 0.0625. Follow along at home if you can. I'm going to take that number and I'm going to multiply it just by hitting the X next, the multiplication sign, because it's already in my calculator. And my calculator says answer times, and I'm going to multiply it by 480, which is my source voltage. And that equals 30 volts. So you can see I could solve this 30 volts by using the proportionality. That is to say, this resistor divided by the total resistance, take that number and multiply it by the source voltage. It gives me that too. Work the same on any of these. If I said 220 divided by 240, 220 ohms divided by 240 ohms, take that number, multiply it by 480, it would give me 440. So that's another way you can do this, and it's a good way to think about this as a proportional system. The proportion is that the bigger resistor drops the bigger voltage proportionally. It takes a bigger bite. This guy is a voltage divider. Remember, series circuit's a voltage divider, and this particular voltage divider takes 3 bites out of the voltage. It takes a big bite from a big resistance. It takes a small bite from the small resistance, and it takes an teeny, all it's got left, the poor guy that gets the 3rd bite, there's hardly any of the candy bar left. It gets this tiny little bite for the smaller voltage drop and resultant power dissipated. So that's that. Let's see how much time I got left on the little timer-oonie here. Of course, I got 13 minutes left, so I got time to talk about some other stuff. I have downloaded the rest of this worksheet. This is a pretty good worksheet. I actually have only downloaded the first 10 problems. There's some story problems after that, but I figured you guys have enough work. So this is a great worksheet. It's got circuits that very closely mimic the kind of circuits that we're going to be working on in class. The book, I've asked you to read 2 chapters. Chapters, was it 5 and 6? I think it's 5 and 6. Yeah, and 5 is like on magnetism or something, but 6 is where the rubber really hits the road, and 6 deals with series circuits. So read 5. It's great information to have. I'm not going to test you on it. You don't need to do any of the problems in 5. In 6, I do want you to do the practice problems, and the review questions. So do the review questions, answer those. No need to submit those to Moodle. And then do the practice problems. Now, the practice problems, actually 5 isn't magnetism, Unit 5 is resistors. And part of what the resistor chapter that I don't need you to learn is the resistor color code. If you want to, you can learn it, but honestly, the print, it's nothing you as an electrician are ever going to need. If you're doing electronics, you need resistor color code to be able to identify resistors. You're not going to need that as an electrician. And the problem with it is the book's printing colors are terrible. It's really hard to tell what colors they are. So I urge you to look into the back of the book. I think it's page 949. It shows you the answers. And hopefully you don't look at all the answers and fill them in because that's worthless. But go ahead and look at what they've gotten for the resistors. Because you don't need to do the try and figure out what color code is. You're going to spend a bunch of time pulling your hair out trying to figure out if it's yellow or orange. And it doesn't matter, as it turns out. Just take the values they give you for R, and then go ahead and work the rest of those questions. I am going to go over on week 3, which to you guys is next week. Week 3, I'm going to go over the homework. I'm going to go over this, and then we're going to go ahead and jump into, we just did series. We're going to do parallel circuits next week. So I hope that makes sense. I am available for a while still. You guys are seeing this maybe first on Friday. I may be available a little bit of Friday. I will be available by text if something completely falls apart. Now, there were 2 people who were absent last week that just didn't show up at all. If you are one of those 2 people, please look at the Moodle. Try to do as much work as you can from what there is in the Moodle. Read the chapters. And then it won't let you take the quiz. You're going to have to get a hold of me and we'll figure out how to make that up. But if you can do this week's work, take the quiz and everything, we can probably still stay on course, on track. What else did I want to tell you about? I think that's it. So 2 relatively short videos. You've got some work to do. Please do it. This is a good time to keep up. We're going to do a lot more interesting work next week. There is another video that you're welcome to watch that takes us back all the way and then he actually goes past this point. It's that makeup video that I made for a class last year. You may watch that if you'd like to. It explains some of this stuff in pretty much the same way and some of it a little bit different. Those of you who missed last week too, you probably want to watch that video because it takes us back into talking about what is an ohm, what is an amp, what is a volt, and what is a watt. Watt is a watt. Anyways, that's it. I will see you at week 3 in the Zoom. Thanks so much.